Yes. Hello, students. All of you, good evening. Welcome to the session. Continuation of network theory. In the last sessions, I discussed in detail about AC analysis that is completed. And today I'm starting a new concept with respect to network theory. That is the concept of resonance. Today and tomorrow session, we'll complete this concept of resonance. Then we'll start with the coupled circuits, then two-port networks. Mainly that concepts, mainly you concentrate, and finally network theorems. Yes, friends, first here I'm giving some introduction. Please concentrate, everybody. This is one important concept for any competitive exam, either GATE or ESC, for any PSUs also. From network theory, this is one important topic. Students, all of you well known this one. Resonance is the frequency response of a circuit or network when it is operating at its natural frequency is called resonance frequency. If any circuit is operating at natural frequency, that frequency is treated as a resonance frequency. Resonance in electrical circuit is because of presence of both storage elements. All of you well know this one, which are the storage elements, inductor and a capacitor. That is, resonance in electrical circuit is because of the both storage elements. Which are the both storage elements? That is inductor and a capacitor. At a fixed frequency, L and C elements will exchange energy freely as a function of time. At a particular frequency, these L and C elements will exchange the energy as a function of time, which results in sinusoidal oscillations either across inductor or capacitor. That is at resonance condition. And resonant frequency indicate the rate at which energy transformation is done between inductor and capacitor. One more significance of resonance frequency is which indicate the at what rate the energy transformation is done between the inductor and capacitor. Under resonance condition, the total supply voltage and supply current is in phase. That later I will give the proof also. Think all of you know this one, students. V and I is in phase. Why? At resonance condition, the circuit is purely resistive. If it is a resistive circuit in the sense, then voltage and currents are in phase. If the voltage and currents are in phase means, what the angle between voltage and current, students? It is a 0 degrees. If the angle between voltage and current is 0 degrees means that circuit, that resonance circuit is operating at what power factor? Unity power factor. And point also remember, there is a maximum power is transferred to the entire circuit by the source under resonance condition. Yes, friends, all these are the introduction points. And one more point to remember, the energy storage components. Which are the energy storage components? That is the inductor and the capacitor. The inductor and capacitor is used in such tuned circuits, that is a LC tuned circuit, must have high quality, which is defined as a quality factor or figure of merit of the coil. That means whatever the L and C we are using in a tuned circuits, in a resonating circuits, that circuit must have the high quality factor. High quality factor. That is a high quality in the sense high quality factor. Here I am giving some fundamental formula. Later on I will give the in detail about this formula. Then here I am giving the quality factor. How to define the quality factor, students? Then Q factor. This is quality factor of a coil. Q factor equal to this is the fundamental formula. This is 2 pi into yes, students. This is maximum stored energy per cycle of supply. Maximum, very important formula, please concentrate. In detail about later that I will give. Maximum stored energy, yes, friends, per cycle of supply. Maximum stored energy per cycle of supply by energy dissipated per cycle of supply. per cycle of supply. Energy dissipated. Energy dissipated. Energy dissipated per cycle of supply. That means if the energy dissipated is more, the quality factor of the coil is less. If the energy dissipated is more, the quality factor of the coil is less. That is the meaning. Yeah, this is the fundamental formula for the quality factor of a coil. Why I am defining here quality factor is, once we are using any tuned circuits, compulsory you can use the L and C. Tuning in the sense we are tuning the frequency. For example, take the example of radios. In radio, we are tuning the frequency. If you want to go for different stations, if you want to go for different stations means we can tune the frequency where we are using the L and C. Generally, whatever the L and C values we are selecting, that L and C values must be high quality factors. But very important for competitive point of view, please concentrate. Later on, I will give the in detail about these formulas. But this is the summary point to remember here. Element and Q factor. Q factor. If you take the element and Q factor, students, if you take a pure resistor, what are the quality factor? What are the quality factor, students? If you take the a pure resistor case, can anybody tell what is the quality factor? There is no any energy storage. A resistor is a completing it is a dissipating element. Completely energy is dissipated. The quality factor equal to 0. If it is a pure inductor, practically not possible. Talking about pure inductor. Pure inductor, what is the quality factor? The resistance is 0. Resistance is 0 means energy dissipation is 0. Energy dissipation is 0 means then quality factor is infinity. If it is a pure capacitor, if it is a pure capacitor, what are the quality factor, students? Infinity. These observations are important for competitive point of view. That's why I'm giving this. Come on, students. If it is a RL combination, series RL combination, if it is a series RL combination, what are the quality factors, friends? Omega L by R. This is also written as XL by R. XL by R. Then element and quality factor. I'm explaining here element and Q factor. Element and Q factor. Next, if it is a series RC combination, if it is a series RC combination, then what is the quality factor you can write, students? The quality factor equal to 1 by omega CR. This equal to XC by R. Sir, how it is 1 by omega CR? That I will give later. But for summary point of view, here I am writing. Yes. If it is a series RLC combination, if it is a series RLC combination, can also write the quality factor. Can also write the quality factor Q equal to, yes friends, one more formula, 1 by R into square root of L by C. 1 by R into square root of L by C. Then if it is a, here one more, element and quality factor. This is element and Q factor. If it is a parallel RL combination, what are the quality factors, friends? This is R, this is L. Then you can write R by omega L. R by omega L, that is R by XL. XL is omega L. It is a parallel RC combination. Parallel RC combination. Then how to write the quality factors, friends? Omega CR. That is R by XC. R by XC. XC is 1 by omega C. That becomes omega CR. It is a parallel RLC combination. RLC combination. Then how to write the quality factor, students? Q equal to, here I written 1 by R into square root of L by C, but here I am writing R into square root of C by L. R into square root of C by L. This is important observations for competitive exam. That's why I given as a summary points. Q equal to R into square root of C by L. Okay, but this is the fundamental formula for quality factor. Direct formula is asked in ESC exam and some other state government jobs point of view also. This direct formulas is important. No need to make any derivations for this competitive point of view. Yes, friends. Okay, this is about some introduction to the resonance concept. But mainly there is a types of resonance. Once we can study the resonance concept in a series circuit, that is called series resonance. We don't have any series resonance, parallel resonance, sir. The types of resonance is the, if it is a series circuit, we are telling that it is a series resonance. But the types of resonance is not a series resonance, parallel resonance. That type we don't have. But name is based on the type of circuit only. Point to remember. This is not based on the type of resonance. This is based on the type of circuit. Once we are studying the resonance in a series circuit, that is called series resonance. Once we are studying the resonance in the parallel circuit, that name is given as a parallel. We don't have any parallel resonance. Understand? Okay, these names are based on the type of circuit. Then all of you well know this one, sir. We are studying this resonance. What is the use of this resonance? Yeah, so many applications are there, sir. But practically, but in our BTech study or in any competitive point of view, we are not analyzing with a practical point of view. Our main motive is we want to understand the theoretical concept. That concept we want to apply to solve the questions in competitive exam. That is our main motive, not for practical understanding. But that all of you know this one, what the applications of a resonance effect. Most common application is tuning. For tuning of the circuits, for example, when you tune a radio to a particular station, the LCs, for example, now you are listening Vijayawada station, and then you want to go for the Tirupati station. If you want to listen that one, then we want to tune that one. We want to change the frequency. If you want to change the frequency, means we want to tune the L and C elements. The LC circuits are set at resonance for that particular carrier frequency. A series resonance circuit provides voltage magnification. Later, we give the proof also. A parallel resonance circuit provides the current magnification. Yes, sir. Important points. A series resonance circuit is the voltage magnification circuit, or it is also called acceptor circuit. Why it is called acceptor circuit? Later, I'll give. A parallel resonance circuit can be used as a current magnification circuit, and it is also a rejector circuit. A parallel resonance circuit can be used as load impedance in output circuit of RF amplifiers, radio frequency amplifier, that well known about the EC students. Due to high impedance, the gain of the amplifier is maximum at resonant frequency. That's the reason why you are using the parallel resonant circuit to get the more gain at the output side. Both parallel and series resonant circuits are used in induction heating. This well known about the electrical students. Induction heating. One of parallel and series resonant circuits are used in the induction heating application. Induction heating means mainly it depends on the current. If you want to get the more currents means then you want to operate at a resonance condition, then you want to get the more current. Okay, this is the applications of the resonance effect. Now we concentrate on the resonance in series circuit. That resonance actually it is called a series resonance, students. It is called series resonance. Here I'm going to writing very important formulas and very important observations also. You please concentrate, students. Yes. Now tell me, at resonance condition, I told already the circuit is the purely resistive circuit. The reason is at resonance, this is the resistor, inductor and capacitor is connected in series. Resistor, inductor and capacitor is connected in series. Let the voltage across the resistor is VR. Voltage across the inductor is VL. Voltage across the capacitor is VC. And the current through the circuit is I, where V is the supply voltage. Where V is the supply voltage, students. Source voltage or supply voltage. It is also called source voltage. Where VR is the voltage across the resistor, VL is the voltage across the inductor, VC is the voltage across the capacitor. And you know this point at resonance condition, one important observation is at resonance, the net reactance equal to zero. The net reactance equal to zero. What do you mean? What is the net reactance here, students? There is inductive reactance and capacitive reactance. Then inductive reactance and capacitive reactance means what are the net reactance? Think all of you know this one. The inductive reactance is the positive reactance. The capacitive reactance is the negative reactance. The reason I told already in the AC analysis why it is a negative for capacitive reactance. Understand? This XL minus XC. The net reactance equal to zero. That means XL equal to XC. This is XL equal to X. This is one observation at resonance condition. This is at resonance condition XL equal to XC, students. Now you tell me all these observations at resonance condition. If XL equal to XC, then what is the Z, students? In RLC circuit, how to write the impedance? Z equal to square root of R square plus XL minus XC whole square. But what is XL equal to XC? Then Z equal to R. Z equal to R. Z equal to R means this is called Z minima. At resonance condition, therefore at resonance condition, this Z is nothing but a minimum impedance. Because these reactances are cancelled, then this impedance is nothing but a minimum impedance. Then that means at resonance condition, we can get the minimum impedance. What is that minimum impedance? Is the resistance. We are getting the minimum impedance, that is nothing but a resistance. At resonance condition, all these are the observations at resonance. All these are the observations at a resonance condition. Point to remember. If the impedance is minimum means, then what is the current at resonance condition? The current at resonance. This is impedance at resonance. Then what is the current at resonance? Current at a resonance condition. Yes, friends. What is the current at resonance condition? The current at resonance condition is I equal to I max. This is I equal to I max. Then what is that I max? V by Z minima. Current is maximum means impedance is minimum. V by what the Z minima, students? R. The current at resonance condition is I equal to V by R. This is at resonance condition. I am writing all these conditions at resonance. Now tell. That is at resonance condition, circuit is purely resistive. At resonance condition, at resonance, because of net reactance equal to zero, at resonance, circuit is purely resistive. Circuit is purely resistive. Then circuit is purely resistive means that is V and I is in phase. V and I is in phase. Then V and I is in phase means that is the supply voltage and current. Then if you draw this one phasor diagram, V and I is in phase. This is V, this is I, and this is the V is in phase. But here this V equal to VR. This is the voltage across the resistor. At resonance condition, V equal to VR. That is the voltage across the resistor because circuit is the resistor. Then what is the angle between voltage and current, students? 0 degrees. If the angle between voltage and current is 0 degrees, then what is the power factor of the circuit? The power factor equal to, the fundamental definition is cos of angle between voltage and current. That is the cos 0. Then cos 0 means what is the power factor? The circuit is operated at unity power factor. The circuit is operating at a unity power factor. Then at resonance condition, to get the complete phasor diagram, at resonance condition, to get the complete phasor diagram, students, see at resonance, All these are the observations at resonance condition. VR equal to V. VR equal to V. Then what is VL equal to? Voltage across the inductor equal to I into XL. I into XL. Okay, this is equal to actually I into JXL. For inductive reactance is the JXL. Then how to write, students? I into XL at angle of which one? 90 degrees. Then what is VC? VC equal to I into minus JXC. You can also write this one I into XC at angle of minus 90 degrees. Then if you draw the complete phasor diagram, this is I, this is the VR. VR equal to V. Voltage and the voltage and currents are in phase. Voltage and current is in phase. This V equal to VR. But what is the voltage across the inductor? The voltage across the inductor, that is I into XL, this is plus 90 degrees. This plus 90 degrees means this is VL. And this is VC. This is minus 90 degrees. That is voltage is leading, but current, voltage is leading, but current is lagging with respect to inductor. With respect to capacitor, voltage is lagging, but what about the current? Current is leading. This is minus 90 degrees. This I am writing. But these two are equal. Why these two are equal, students? Because the current is I, but XL equal to XC. At resonance condition, XL equal to XC, then what is I into XL equal to? I into X. I'm talking about the magnitudes. This is equal to VL equal to VC. The magnitude of voltage across the inductor equal to magnitude of voltage across the capacitor. Yeah, this is the plus 90 degrees and this is the minus 90 degrees. Yes, students, any doubt? But magnitudes are equal, sir. But what is the net reactive voltage? I'm talking about net reactive voltage. That net reactive voltage equal to 0. The net reactive voltage equal to 0. What is the net reactive voltage, sir? If you take the net reactive voltage, all these are the observations at resonance conditions, sir. At resonance, what is the net reactive voltage? Net reactive voltage. Can anybody? Then net reactive voltage VL plus VC. What is VL, sir? J into IXL minus J into IXC. With respect to capacitive reactance is negative. That I have to explain the AC analysis. Minus J into IXC. But XL equal to XC at resonance condition. XL equal to XC or XC equal to XL, you can substitute. What this resultant value? It becomes 0. The net reactive voltage equal to 0. At resonance condition, the net reactive voltage equal to 0. Yes, students, please concentrate, everybody. And one more observation. At resonance, this is important. At resonance, XL equal to XC. I told that XL equal to XC. Then the circuit is operating, let us assume that F0 frequency or omega naught angular frequency. Omega naught into L equal to omega naught into, that is 1 by omega naught into C. 1 by omega naught into C. Then from this one, what is the omega naught square, students? 1 by LC. Then what is omega naught? Omega naught equal to 1 by root LC. This is the frequency at resonance, angular frequency at resonance condition. Angular frequency at resonance condition. Angular frequency at resonance condition. What are the units? What are the units, sir? In radians per second. Then once you know the omega naught equal to 1 by root LC, then what is F naught equal to? Omega naught I am writing as a 2 pi F naught. How to write omega naught, students? This I am writing as a 2 pi F naught is equal to 1 by root LC. Then F naught equal to 1 by 2 pi root LC. This is the in cycles per second. This is in cycle per second or H. This we can write in cycles per second or in H. Okay, this is the resonating frequency or frequency at resonance condition. This is the resonating frequency or frequency at a resonance condition. Frequency at a resonance condition. Yes, friends, come on, all of you note down this. Now I want to write different curves at resonance condition. What are the different curves at resonance condition? That is also important. But point to remember, we know that XL equal to, we know that, yes friends, XL equal to omega L, that equal to 2 pi FL. XC equal to 1 by omega C, that equal to 2 pi, 1 by 2 pi FC. 1 by 2 pi FC. Z equal to square root of R square plus omega L minus 1 by omega C whole square. Okay. And I equal to V by Z. Then from these observations, tell the students, at low frequencies, that is frequency is low, at low frequencies, that is F is the low values. Then which is more dominant at low frequencies? Because XL is proportional to frequency, X is inversely proportional to frequency. XL is reduces, XC is increases. That means which is more dominant? XC greater than XL. If XC greater than XL means, you see this one impedance term, students, XC greater than XL. This I am writing simply square root of R square plus XC minus XL whole square. If XC greater than, XL minus XC whole square. XL minus XC whole square. If XC greater means, come on, at low frequencies, if XC greater means negative term is greater. Then what is the R square plus, what is the square root of R square plus XC minus XL, students? XC is greater. It is XL minus XC. Negative term is greater. If negative term is greater, then what this value? Reduces. What this term indicate? That is Z is reduces. At low frequencies. At low frequencies, Z is reduces. Then at high frequencies, if Z is reduces, what the current? Increases. At high frequencies, come on students. At high frequencies, now tell me, this is XC is inversely proportional to frequency. Please remember this one. XL is proportional to F, but XC is proportional to 1 by F. At high frequencies, XC is reduces, but XL is increases. That means XL is greater than XC. If XL is greater than XC, square root of R square plus XL minus XC. Come on, students. This term is increases or decreases? If XL greater than XC means this positive term is more. This is increases. That is Z is increases. If Z is increases, what about I? Reduces. This is for low frequencies. This is for high frequencies. But at a resonating frequency, this already you know. At resonating frequency, Z equal to R. Z equal to R. That is the Z minima. This point already you know. That is Z minima. And I equal to I max. That equal to V by R. V is the supply voltage. Now with this observation, now if you draw a graph between different graphs for resonance point, concepts point of view, graphs also very important. Understanding the graphs is also important. This is with respect, all these concepts are with respect to series RLC circuit. Now if you draw the graph between, come on students, Z versus omega. First I am drawing the graph between Z versus omega. Okay, this is omega and this is the Z. On x-axis I taken omega, y-axis I taken the Z. This is the magnitude of Z. Then if you draw the graph, if the at low frequencies impedance is reducing, at high frequencies impedance is increasing, then you can get the graph like this. At low frequencies impedance is reducing, at high frequencies impedance is increasing. Yeah, this is the explanation. At low frequencies impedance is reducing, at high frequencies impedance is increasing. Then this frequency, this is the point corresponding to which frequency? This is the point corresponding to resonating frequency. Omega naught 1 by root LC. That is F naught 1 by 2 pi root LC. This is the point, minimum impedance point. This is R. This point equal to Z minima point. This is a minimum impedance point. That Z minima is nothing but a R. Z minima is nothing but a R. Okay, this portion, which is more dominant? This portion, which is the dominant, students? Which is the dominant? XL greater than XC. This portion is, which is the dominant? XC greater than XL. Then corresponding to this portion, this point is the corresponding to which one? XL equal to XC, resonant condition. Clear, sir? Any doubt? Okay, this is for impedance curve. Z versus omega curve. Now I want to draw the I versus omega curve. I versus omega curve. Come on. This is omega and this is I. Even F versus Z, F versus I also same, sir. Yes, friends. I told already, impedance is reducing means current is increasing. At low frequencies, current is increasing. At high frequencies, current is reducing. But the width of this curve depends on L and C values. Okay, this is the point corresponding to which frequency? Resonating frequency. This is for omega equal to omega naught. That equal to 1 by root LC. This is also equal to F naught equal to 1 by 2 by root LC. This point is corresponding to which current, students? Come on. This point is corresponding to which current? Maximum current. Okay, this is I max. Then what is this I max? It's V by R. V is the supply voltage, where I max equal to V by R. But point to remember, friends, the width of this curve. What is this width? Generally, here we can define the bandwidth. Later on that I will explain. This also mainly depends on the what type of coil we are using. For example, this observation is important. This type of curve you can get for low resistance, high quality factor. If the quality factor of the coil is less, we may expect the curve like this. This type of curve we can get for high resistance, low quality factor. High resistance and low quality factor. Low quality factor. We can expect the curve like this. Is okay, students? Any doubt here? This is the case for how to draw the curve for this is I versus omega curve. And this is the curve Z versus omega curve. This is the case of resonating condition. This is the case of at resonance condition. This is the point corresponding to XL equal to XC point. XL equal to at XL equal to XC, that is omega naught we are getting. Okay. Now I want to draw the how these reactances are changing with respect to frequency. Z versus omega curve I drawn, I versus omega curve I drawn. Similarly, you see the X versus omega curve. This is also important for competitive exams. X versus omega curve. Yes, friends, concentrate. Easy to understand. Here I am drawing the X versus omega curve. Yes. And this x's I taken omega. This is plus x. Plus x is nothing but a positive reactance. This is plus x. Negative reactance is nothing but a capacitive. This is minus x. Okay. The capacitive reactance equal to xc equal minus xc equal to minus 1 by omega c, sir. The inductive reactance is plus xl equal to omega l, sir. Now if you draw the, if omega is increases, what is xl, students? Increases. Here if omega is increases, what is xc, students? Reduces. Then if you draw the curve, this is the, if omega is increases, xl is also increases. Okay, this is the case of which curve? This is the XL curve. XL. Then what about this is negative? For example, if the omega equal to 0, if omega equal to 0, what is XC? This is infinity. That means it start from this point. At a particular, we don't have, that is it start, the curve is started from infinity. I don't know that point. Then slowly it is decreasing. Slowly it is going to decreasing. Then we can get the curve like this. Then this is which curve, sir? Sir, why you take a negative side? Because the capacitive reactance is negative reactance. Then I am getting the curve like this. This is the capacity. This is the capacitive reactance, Xc. If omega tends to infinity, Xt tends to 0. If omega tends to infinity, Xt tends to 0. That is the meaning. This is Xc curve. But what are the X net, students? What is the X net? Net reactance is X net equal to XL minus Xc. Then if you want XL minus Xc, yes, this is the net reactance curve. If you take the difference between these two, then I will get this net reactance curve is like this. At a particular frequency, what is the XL minus Xc? Is 0. At a particular frequency, the XL minus Xc equal to 0. Then what is that frequency? Resonating frequency. Here I am drawing this reactance, net reactance curve. Okay, this is the net reactance curve. Then this is which frequency, students? Let us to make, it is better to take one more point instead of this. Yeah, this is the point taken as a omega naught, corresponding to omega naught. This is the reactance curves. I draw the current curve, impedance curve, and also the reactance curve. This is at omega naught frequency. This is corresponding to unity power factor, at unity power factor. But if you go this side, which power factor is increases? And if you go for this side, which power factor is increases? For this side, which is more dominant, students? XL is more dominant. XL is more dominant. Then which power factor? Come on. Which is more lagging power factor is increases. If you go this side, then which power factor, which is more dominant? Xc greater than XL. Which power factor is increases? Leading power factor is increases. Sir, all these observations are important for competitive exams. Leading power factor is increases. Clear, friends? Any doubt? That means for omega less than omega naught, for omega less than omega naught, omega less than omega naught, what is the Z? R minus, which is more dominant? For omega less than omega naught, which is more dominant, sir? Capacitive is more dominant. Xc greater than XL. Then net reactance is positive or negative? Sir, net reactance is 0 only at resonance condition. This net reactance is positive or negative? Negative. Xc greater than XL. Okay, negative. The net reactance is negative. Yes. Yes, friends. The net reactance is negative. Then I leads V. Xc greater than XL, I leads V. Current leads the voltage. Current leads the voltage by angle of pi. That pi may be less than 90 degrees. Okay, but it is not a purely capacitive. It is not a purely inductive. But there is a capacitive and inductive is there. But Xc is more dominant. I leads V. Current leads the voltage by angle of 90 degrees. That means it is operating at what power factor? Leading power factor. It is operating at what power factor? Leading power factor. If you make the phasor notation, yeah, this is V and this is the I. I leads V by angle of pi. Then this pi is I leads V. We are measuring this angle clockwise or anti-clockwise, sir? Reference is V here. I leads V. Leading means this one. The vector rotation is always in anti-clockwise direction. Now we can going this side. This concept I explained the AC analysis also. Then we are going to in which direction? Anti-clockwise or clockwise direction? This we are going to which one, sir? Counter-clockwise. That is anti-clockwise. If the angle is measured in clockwise direction, you can take that angle is positive angle or negative angle. Come on. If you measure the angle in clockwise, anti-clockwise direction, you take that angle is positive. That's why for omega less than omega naught, then what the angle, students? What the angle? Positive or negative? This angle is positive for omega less than omega naught. Yes. For omega greater than omega naught. For omega greater than omega naught, sir. Yes, very important to draw the curve. This I am explaining the explanation for this observation I am giving. For omega, it's a greater than omega naught. XL greater than XC. That is current lacks the voltage. Current lacks the voltage. Current lacks the voltage. By angle of pi, that is less than 90 degrees. Then if you represent the vector notation, phasor notation, okay, this is the voltage. The reference is voltage. This is V. Yes, friends. Then current is lagging. Current is going this side, lagging side. Okay, this is I. Then we are measuring this side. We are going this side. This is pi. That means we are measuring in which direction? Clockwise direction. We are measuring clockwise direction means pi is negative. We are measuring clockwise direction means pi is negative. Understand? This is pi is negative. Yes, at omega equal to omega naught. That is at resonance condition. If omega equal to omega naught, what is pi, students? V and I is in phase, that already you know, in phase. Then pi equal to 0 degrees. Then if you draw the, with this observation, if you draw the phase plot, not the magnitude plot, I am drawing the phase plot. I am drawing the phase plot. For this, to draw this plot only, I given all these observations. This is omega versus phase angle. All of you know omega versus V, omega versus I, omega versus Z, omega versus X. Similarly, now we'll see the omega versus phase angle. Omega, this we can expect for computative point of view. Let this point is omega naught, students. Corresponding to omega naught, the power factor is the unity power factor. This is the point corresponding to omega naught. The angle is 0 degrees. The angle is 0 degrees. But here, pi is positive. Pi is positive. Pi is positive for which one? Pi is positive for which one? Reactive, that is capacitive or inductive? That leading case. Let this is the, for pi equal to 90 degrees, for purely capacitive, it's going to decreasing like this. And it is pi equal to minus 90 degrees for inductive. We can get the curve like this. This is the phase plot. This is for minus 90 degrees. This is for plus 90. Then this side is which one, students? Leading or lagging? Leading. This is for XC greater than XL. This side for which one, students? Lagging. Because we are getting negative angle. Negative angle for which one? Omega greater than omega naught. For omega, if you want to this one, omega less than omega naught, this is the positive angle. Omega greater than omega naught, that is the negative angle. This we are getting for negative angle for which one, students? For omega less than omega naught. For omega less than omega naught, yes, for omega greater than, that is less than omega naught means this is for omega greater than omega naught. This is for omega naught. At omega naught, the pi equal to 0 degrees. This is the phase plot under resonance condition in a resonating circuit, series RLC circuit. Yes, friends. All of you understand? Any doubt, sir? Any doubt? We can also draw the curve like this for RLC circuit. If you take this curve like this, also you can draw. Yes, friends. It's not required. Okay, we go for before that we go for one more topic. Later on, I will give that curve. Later on, I will explain that curves. Yes. Yes, friends. Now tell me. Here I am giving very important observations. Yes. Variation of voltage across passive elements with change in supply frequency. Yes. Variation of voltage across inductor and capacitor. Variation of, very important, voltage across inductor and capacitor. Inductor and capacitor for change in frequency. I want this curve. Then for that, first first some conditions. Very important for computer exams. That I want what is the variation of voltage across inductor and capacitor for change in frequency. Yes, friends. First you tell me. What is the voltage across the capacitor? Can anybody? Yes. We know this one for capacitor. First I am explaining for capacitor. Very important formulas we can get here. Vc equal to I into Xc. Okay. Vc equal to I into Xc. But what is I, students? At resonance condition, you know that I equal to V by R. But generally in that series circuit, what is I? V by square root of R square plus XL minus XC whole square. Okay. This is the into XC. V into XC. I into XC. No? I is V by, this is not at resonance condition. In a series RLC circuit, this is at V by square root of R square plus square root of R square plus XL minus XC whole square into XC. Okay. Now I want the frequency at which the maximum voltage appears across the capacitor. At which frequency the voltage across the capacitor is maximum. We are changing the, if you change the frequency up to resonating frequency, after the resonating frequency, at what frequency the voltage across the capacitor is maximum. Then for that, what you can do, students? To get the frequency, at which voltage across the capacitor is maximum. Voltage across the capacitor is maximum. Across the capacitor is maximum. What you can do? To get the frequency, voltage across the capacitor is maximum. Just we can differentiate this equation dvc by d omega and equate to 0. Differentiate that relation with respect to omega and equate to 0. Then we can get, I'm not giving the derivation, is not required. Then I'm giving the FC. This is the frequency at which voltage across the capacitor is maximum. The frequency at which voltage across the capacitor is maximum 1 by 2 pi root LC. 1 by 2 pi root LC, very important formula. Sir, how I am getting this one? Differentiate with respect to omega and equate to 0. This VC already you know. This into, yes friends, 1 by 2 pi root LC into square root of, this is square root of 1 minus r square c by 2l. R square c by 2l. R square c by 2l. Okay, this is the formula you can get. You also write like this. Fc equal to, what is 1 by 2 pi root LC, students? F naught. Square root of 1 minus r square c by 2l. Very important formula for gate point of view. I'm writing 1 by 2 pi root LC is F naught. Okay, what is this one? This is the frequency. This is the frequency at which a maximum voltage appear across the capacitor. This is a frequency at which voltage across the capacitor is maximum. Voltage across capacitor is maximum. That means at this frequency, the voltage across the capacitor is maximum. Capacitor is maximum. Okay. Similarly, I want to find what is the frequency at which voltage across the inductor is maximum. Yeah. Now see for inductor. I want to write for inductor. How to write, friends? For inductor, VL equal to I into XL. I into XL. What is I? That you know, V by square root of R square plus XL minus XC whole square into XL. This is into XL. Now tell this, friends. The frequency at which voltage, to get the frequency at which voltage across the inductor is maximum, to get the frequency at which voltage across the inductor is maximum, what you can do? Voltage across inductor is maximum. Differentiate, same concept, differentiate the voltage across the inductor with respect to omega and equate to 0. Then we can get the expression, yes friends, FL equal to, yes, we can get the expression FL equal to, this is the frequency at which voltage across the inductor is maximum, 1 by 2 pi root LC. Yes, 1 by 2 pi root LC into square root of 1 minus R square C by TL. Yes. Just a minute. 1 minus r square c by 2l. Yes, friends. What is 1 by 2 pi root LC? F naught. That is F naught by square root of 1 minus r square c by 2l. This is F naught into, this is F naught by, yes, square root of 1 minus r square c by 2l. Okay, this is the frequency at which voltage across the inductor is maximum. This is the frequency. Sir, how I am getting this one, sir? Just differentiate and equate to 0, sir. Frequency at which voltage across inductor is maximum. Inductor is maximum. Inductor is maximum. Now see, with this observation, if you draw the curve between voltage versus frequency, I drawn the current versus frequency, impedance versus frequency, reactance versus frequency, and phase versus frequency, phase angle versus frequency. Now I am drawing the voltage versus frequency. I am drawing the curve between voltage versus frequency. Every curve is important for competitive point of view. Yes, friends. Drawing the curve between voltage versus frequency. This is frequency F, and this is the V, is the voltage. Now tell me, first I am drawing the a curve of a supply voltage. We are giving the a supply voltage. Let there is no change in the supply voltage. Let this is the constant voltage. There is no change in the supply voltage. That is the meaning. There is no change in the supply voltage. Don't think it is a constant DC voltage like that. We are not changing 230 volts, 50 hertz AC supply, for example. Then 230 volts is constant. That 230 volts. That is the meaning. This is the supply voltage. Yes, friends. Then this is the frequency at which voltage across the capacitor is maximum. Let this is the frequency at which voltage across the capacitor is maximum. That is FC. Let this is the frequency is the F naught frequency. This frequency is the F naught frequency, resonating frequency. And this is the frequency at which voltage across the inductor is maximum. This is FL frequency. Then we can get the approximately the curve is like this. Yes, friends. We can expect the curve like this. I'm drawing the variation of voltage across the capacitor with respect to frequency. Variation of the voltage across the capacitor with respect to frequency. Let this is the maximum. Voltage across the capacitor is maximum. Then it's going to decreasing like this. After reaching the maximum value, it compulsory decreases. Yes. Just a minute. Later on that I will represent this curve. Yes, friends. After reaching the maximum value, the voltage across the capacitor is reducing. And this is the voltage across the inductor going to increasing. Yes. Yes, students. This is the voltage across the inductor is maximum going to decreasing. And this is the frequency corresponding to FL. This is the frequency at which voltage across the inductor is maximum. And this Vc equal to VL at which frequency? We know that Vc equal to I into Xc, but at omega naught, at omega equal to omega naught, Xc equal to XL. If Xc equal to XL, Vc equal to I into XL, this is equal to VL. Vc equal to VL at what frequency, sir? Resonating frequency. This is at a resonating frequency. And at resonating frequency, at this frequency, what the voltage? Corresponding to this voltage, corresponding to, yes, at this frequency, the voltage is equal to supply voltage only. Then the curve is, this is the variation of the voltage is which voltage? Resistive voltage. This is VR curve. This is VL curve. And this is VC curve. Sir, how I am getting this curve, sir? Just you take this one. Take the voltage across the inductor, voltage across the inductor. Substitute the frequency changes here. Then we can get this curve. And this is voltage across the inductor. Substitute that different values of frequency. Then we can get this curve. But I want the maximum points only. This is the frequency at which voltage across the capacitor is maximum. And this is the frequency at which voltage across the inductor is maximum. This is the curve at which voltage across the inductor is maximum. Yes, friends. Now you have the doubt here, sir. For low frequencies, why the capacitor voltage is maximum? For high frequencies, why the capacitor voltage is inductive voltage is maximum? This is for omega greater than omega less than omega naught, sir. This is for omega greater than omega. If you want that observation, students, see for example, if you take the inductor or if you take the capacitor. For example, first I am explaining the inductor. You can try for capacitor also. You can try for capacitor. Yeah, first here I am explaining the inductor case. For example, you take the for low frequencies. For low frequencies. For low frequencies, that is omega less than omega naught. Omega less than omega. Low frequencies in the sense omega less than omega naught. Then Xc is increasing or reducing? Reduce. XL is which one, students? XL is increasing. For low frequencies, Xc is, I'm talking about the F is low value. F is low value means Xc equal to 1 by 2 pi Fc. Understand? Or otherwise, simply you take for low frequencies, what about I, sir? This is for low frequencies, Vc equal to I into Xc. I into Xc. For low frequencies, Xc is greater. Then Vc is greater. For high frequencies, that is omega greater than omega naught. VL equal to I into XL. For high frequencies, XL is greater. Then VL is greater. That's the reason why at high frequencies, we are getting the voltage across the inductor is maximum. At low frequencies, voltage across the capacitor is maximum. Voltage across the capacitor is maximum. Okay, these are the different curves with respect to resonance circuit. And one more observation, students, please concentrate. At omega equal to omega naught, very important point here. At omega equal to omega naught, what is VR? Voltage across the resistor, that is I into R. That I is I max into R. That I max equal to V by R. That I max equal to V by R into R. That is VR equal to V. Correct? Voltage across the resistor equal to supply voltage. Then what is the voltage across the inductor, students? VL equal to, come on, J into I into XL. J into I into XL. This I will write like this. Yes. J into I is V by R. XL is omega naught into L. Omega naught into L. Shall I write like this? J into omega naught into L by R into V. Then how we can write this one? J omega naught L by R is Q. That is Q into V. This is plus J Q, where Q equal to quality factor. Omega naught into L by R. If you take the capacitor, what is Vc, students? Minus Ji into Xc. Shall I write like this? Minus Ji is V by R. Xc is 1 by omega naught C. Correct. X is 1 by omega naught C. Shall I write like this? Minus J 1 by omega naught C R. What is 1 by omega naught C R? It's a, which one, sir? Into V. V is there now. Minus J QV. This is minus J QV. Yeah, this is negative. This is the positive. That means VL equal to Q. If you take the magnitude, VL equal to QV. If you take the magnitude, Vc equal to QV. That means at resonance condition, VL equal to Vc. At resonance condition, the magnitude of voltage across the inductor equal to magnitude of voltage across the capacitor, but it is not equal to supply voltage. It is the Q times of the supply voltage. Therefore, under series resonance condition, then under series resonance condition, what is the voltage across L and C components, students? Q times the supply voltage. Therefore, at series resonance condition, come on, students. Voltage across inductor and capacitor. Voltage across inductor and capacitor. Which one? Q times the supply voltage. Q times, where Q is the quality factor. Quality factor. Here also Q equal to 1 by omega naught CR. Q times the supply voltage. Q times the supply voltage. Hence, this circuit is considered as a voltage magnification circuit. Hence, this circuit is considered as a voltage magnification circuit. Voltage magnification circuit. Okay, this is the reason why a series circuit is a voltage magnet. That is by changing the Q. If Q changes, voltage across the inductor it changes. If Q changes, voltage across the capacitor it changes. This is the voltage magnification circuit. And one more point to remember: under series resonance condition, the net impedance is minimum, current is maximum. That means it accepting the maximum current. It accepting the maximum current means hence it is also called as a acceptor circuit. Under series resonance condition, yes friends, which one? The net impedance is minimum. Net impedance is minimum. Net impedance is minimum. And current is maximum. And current is maximum. Yes. Hence this circuit is, hence it is a acceptor circuit. Hence it is an acceptor circuit. These 2 points important with respect to series resonance circuit. Yes, friends. Okay, this is about what exactly observations from the resonance circuit, series resonance circuit. But here I want to define one term that is also important. Generally, the series resonance phenomena was used in design of passive analog communication, and we also used in, that is the analog communications of receivers and antennas. For design of receivers and antennas in analog communication, that you well known about the EC students. Okay, that we can use this series resonance concept. The example is, if you take the old radios. In old radios, for tuning the frequency, we are using this series resonance. Okay, then here I want to explain bandwidth. Very important. What is the bandwidth with respect to series resonance? That expressions also very important formulas to solve the problems. Yes, friends. Bandwidth, one concept, and selectivity is also one more concept with respect to resonance. Then after completing that one, we go for the parallel resonance. That means how to define the bandwidth, student? Bandwidth represents the range of frequencies. You please note down this one. Bandwidth represents the range of frequencies. Range of frequencies. Range of frequencies for which the power level in the circuit is at least, for which the power level in the circuits is at least 1 by 2 of maximum power. Yes, friends. The power level in the you take the power level in the signal. Signal is at least 1 by 2 of maximum power, 1 by 2 of maximum power, yes friends, that the circuit can handle, okay. That generally this is the definition for bandwidth. A bandwidth is nothing but a range of frequencies, but that range of frequencies are defined at which the power level is 1 by 2 of the maximum power level. Actually, that frequencies are taken as a at cutoff frequency. That is at cutoff frequency. At cutoff frequency, what is the power, students? P equal to P naught by 2. P equal to P naught by 2. That is power at resonance condition you take. P naught is the power at resonance, or you take the P maxima by 2. P maxima by 2. At resonance condition, maximum power is transferred. P maxima by 2. Shall I write like this? P maxima equal to I maxima square into R by 2. I maxima square, yes, R into 2. Then what is this? Shall I write like this? I maxima by root 2. I maxima by root 2 whole square into R. That means power is P maxima by 2 means current is I maxima by root 2. That's the meaning. At cutoff frequency, this is the current at a cutoff frequency. At a cutoff frequency. Correct, sir. The power is P maxima by 2 means current equal to I maxima by. That I maxima square by 2 I am writing as I maxima by root 2. Once again you simplify this one, you can get this. Then if you represent this curve, omega versus I curve. This curve you already know. I drawn already. Then this is the corresponding to omega naught. Corresponding to omega naught. Let this current is the I max. Then I maxima by root 2. This you take, this is the point. I maxima by root 2. Corresponding to this current, whatever the frequencies are there, this is the cutoff frequencies. Let this is the omega 1 and this is the omega 2. This width is nothing but which one, students? What is this width? This is which one? Is the bandwidth. Sir, why you taken this? According to the definition, this is P maxima by 2. P maxima by 2 means I maxima by root 2. Then at this current, whatever the frequencies are there, cutoff frequencies, this is the lower cutoff frequency, this is the upper cutoff frequency. Lower cutoff corresponding to bandwidth, this is the upper cutoff frequency. This is upper cutoff frequencies. Okay, this observation is important. Yes, friends, please concentrate. Omega 1 is the lower cutoff frequency, omega 2 is the upper cutoff frequency. That means I equal to I maxima by root 2. At cutoff frequencies, I equal to I maxima by root 2. Then from this, we'll see some important formula. That is at a cutoff frequencies, at cutoff frequencies, I equal to I maxima by root 2. Is it correct, sir? But what is I in this circuit? V by square root of R square plus XL minus XC whole square. This is equal to I maxima by, what is I max? That is the current at resonance condition. Current at resonance condition. This VV cancel. Then what we can get, students? The square on both sides, R square plus XL minus XC whole square is equal to 2R square. Square on both sides, students. Then what is X? Very important formulas we can get here. XL minus XC equal to R square. XL minus XC whole square equal. This R square, you bring this side, we can get the R square. Then from this, what is XL minus XC, sir? This is plus R minus R. XL minus XC equal to plus R minus R. Here we can write two formulas. This we also write this one omega L minus 1 by omega C is equal to plus R minus R. Now see, at a lower cutoff frequency, at upper cutoff frequency, at omega equal to omega 2, that is at a upper cutoff frequency. Upper cutoff frequency. Then upper cutoff frequency is which is more dominant, students? Inductance is more dominant. If inductance is more dominant, then this term is greater than this term. This gives the positive resistance. Yes or no? Then omega 2 into L minus 1 by omega 2 into C. This is equal to plus R. Sir, why you taken plus R, sir? That is at omega equal to omega 2 means upper frequencies, upper cutoff frequency. Upper cutoff frequency is omega 2 is greater than omega naught. Then which is more dominant? XL is dominant. Clear or not? XL is dominant. That's why XL is dominant means this is more as compared to this one. This gives the positive. Clear or not? Let this is the one equation. Let this is the equation one, sir. At omega equal to omega 1. At omega equal to omega 1. That's a lower cutoff frequency. That lower cutoff frequency is omega 1 is less than omega naught. No? Then XC greater than XL. XC greater than XL means which is more dominant, students? Reactive, that is capacitive reactance is dominant. This is the dominant means we can get the negative value. This difference we can get the negative value. That's why omega 1 into L at lower cutoff frequencies, omega 1 into L minus 1 by omega 1 into C is equal to minus R, sir. Understand or not? Not only final formula, students, in between whatever the concept I am explaining, that you concentrate. Let this is the equation 2. Then I am doing 1 plus 2. What you can get? Omega 1 into L, omega 2 into L minus 1 by omega 2 into C plus omega 1 into L minus 1 by omega 1 into C is equal to R minus R. This equal to 0. Is it okay? Take the L is common, students. Omega 1 plus omega 2, sir. Yeah, minus 1 by C is common. If you take the minus 1 by C is common and you simplify that one, what you can get? Omega 1 plus omega 2 by omega 1 into omega 2 is equal to 0. Yes. From this one, L into omega 1 plus omega 2 is equal to 1 by C into omega 1 plus omega 2 by omega 1 into omega. These two cancels. Then what is we can get, students? 1 by LC equal to omega 1 into omega. But we know that what is omega naught square? What is omega naught square, students? 1 by LC. That I am replacing here. Then omega naught square equal to omega 1 into. Very, very important formula, 5-star formula. Then the resonating frequency is the geometric mean of the cutoff frequencies. Correct or not? Which one, sir? The resonating frequency. Or you also write this one. F naught equal to square root of F1 into F2. That is also correct. Just you substitute 2 pi F1, 2 pi F2, S. Then 2 pi you can bring outside. 2 pi will cancel. We can get F naught. Therefore, the resonating frequency is the geometric mean of cutoff frequency. Very, very important 5-star relation. The resonating frequency is geometric mean of which one, sir? Cutoff frequencies. Clear, friends? Okay, this is one observation from the bandwidth. And we can also get one more expression here. One more expression also we can get. Please concentrate. I done 1 plus 2, but if you do the 1 minus 2, that is, we can get L into, by simplifying that, we can get what is 1 minus 2, students? 1 is omega 2 into L minus 1 by omega 2 into C minus omega 1 into L minus 1 by omega 1 into C. If you do 1 minus 2, R minus R, this we can get 2R, sir. Previously, that is addition, R plus R minus R is 0. But here, R minus R, we can get the 2R. Then in this case, you take the L is common, omega 2 minus omega 1. Minus 1 by C is common, and simplify that one. Omega 2 minus omega 1 by omega 1 into omega 2. Okay, omega 1 into omega 2. Okay, this is equal to 2R. Yes, friends. From this one, you take omega 2 minus omega 1 is common. If you take omega 2 minus omega 1 is common, this we can get L yes, just a minute. You are taking the 1 by C is common. Minus 1 by C is common, or plus 1 by C is common. 1 by C is common. Then 1 by omega 1C minus 1 by omega 2C. Then omega 2 minus this, I think it is a plus 1 by C. Is it correct, sir? Then you take L plus 1 by C into omega 1 into omega 2. Just mathematical simplification only, sir. Nothing is there. Yes, L plus C into omega 1 into omega 2. But you know this, sir. What is omega naught or omega 1 into omega 2? Omega 1 into omega 2, omega naught square equal to 1 by LC, that equal to what I written students here, is equal to omega 1 into omega 2. This you know. That I am replacing omega 1 into omega 2 equal to 1 by LC. Then omega 2 minus omega 1 into L plus 1 by C into 1 by LC is equal to 2R. Then from this one, you simplify this one, CC cancel, 2L we can get. Then omega 2 minus omega 1 into this 2L equal to 2R. 2 cancel. What is omega 2 minus omega 1, students? Yes, very good. This is equal to R by L. This is equal to R by L. This is in radians per second. Because is the cutoff frequencies, omega 2 minus omega 1 equal to R by L. What is that omega 2 minus omega 1 is called? Which one, sir? Therefore, omega 2 minus omega 1 is which one? Is the bandwidth. The bandwidth, one of the formula for bandwidth equal to R by L. Very, very important 5-star formula. R by L. We can also write omega 2 is 2 pi f2, omega 1 is 2 pi f1 is equal to R by L. Then f2 minus f1, this is also called bandwidth. R by 2f, R by which one? f2 minus f1 equal to, yes friends, R by 2 pi L. That 2 pi you can bring this side. This is in, what are the units for this one? f2 minus f1 in hertz or cycles per second. This is in terms of radians per second. This is in radians per second because of it is the difference between the angular frequency. This is the difference between the, that is the frequency in hertz or cycles per second. That means what is the observation here, sir? Bandwidth depends on the resistance, but resonating frequency is independent of the resistance. Is correct or not? That means f naught equal to 1 by 2 pi root LC. This is a resonating frequency. But what are the bandwidth, students? Bandwidth equal to omega 2 minus omega 1, that equal to R by L. Therefore, bandwidth independent of the resistance, but bandwidth is proportional to R. That means bandwidth is independent of the resistance. Bandwidth depends on the resistance. Bandwidth depends on resistance. But resonating frequency independent of the resistance. But resonating frequency independent of resistance. Is it correct or not? Is there any resistance term here? No. Independent of resistance. Yeah, this is about what exactly the concept of bandwidth. So once you know the bandwidth, but what are the cutoff frequencies? By knowing the cutoff frequencies only, you can find the bandwidth. Then for that, we have two equations are there, two unknowns. We know that what is omega 2 minus omega 1 is equal to R by L. What is omega 1 into omega 2? Come on. What is omega 1 into omega 2, sir? 1 by LC. These are the two unknowns. By solving these two equations, we can get the two unknowns. Two equations, two unknowns we can get. Two equations, we can get cutoff frequencies. We can get omega 1 and omega 2. We can get omega 1 and omega 2. Then what are the expressions for omega 1 and omega 2? That I'm not giving derivation, directly I'm giving. Just a minute. Then we can write the what is the omega 1 value and what is the omega 2 value. That is nothing but a cutoff frequencies we can get. But I want to find the what is the omega 1 expression and what is the omega 2 expression. Yes. Okay. This is about the, you can solve this one, omega 1 and omega 2 we can get. Any doubts, friends? If you have any doubts up to now, whatever I explained, can anybody respond? Yes, friends? Any doubt? Nobody is responding. Is it okay? Yes. I'm adding one slide, please. Just a minute. I want to complete this omega 1 and omega 2 expressions also. Just a minute. Just a minute. Yeah. When I want to solve these equations means, first I want to find, once you know the omega 2 minus omega 1, students, then how to find the omega 2 plus omega 1. Shall I write like this? Omega 2 plus omega 1 equal to just mathematics only. If you want a plus b means square root of a minus b whole square. A plus b want square root of a minus b whole square plus what you can get 4ab, 4 omega 1 into omega 2. Is it correct? This omega 2 plus omega 1. Just mathematics only. If you want a plus b, square root of a minus b whole square plus 4ab. You simplify this one, you can get this one. Understand? Then what is omega 2 minus omega 1? R by 2l. Is it R by L? Omega 2 minus omega 1, students. Then what I calculated? that is R by L. I calculated R by L whole square. What is omega 1 into omega 2? Omega 1 into omega 2 equal to 1 by LC. This is R by L whole square. This is 4 into, what is omega 1 into omega 1 by LC? This is equal to square root of R by L whole square plus 4 by LC. 4 by LC. Okay. Then omega 1 minus omega 2 minus omega 1 equal to R by L. Omega 2 minus omega 1 equal to R by L. Omega 2 plus omega 1 equal to square root of R by L whole square. R by L whole square plus 4 by LC. 4 by LC. Okay, this also write like this, 4 by LC. Yes, shall I write like this one? If you take the 4 is common, R by 2L whole square. If you take the 4 is common, 2 into, just small modification here, 2 into square root of R by 2L whole square. If you take the 4 is common, R by 2L whole square plus this 1 by LC, I am writing 1 by root LC whole square. Okay, this is omega 2 plus omega. Then I want add these two. If you take, let this is the one equation and this is the another equation. If you take 1 plus 2, we can get 2 omega 2. 2 omega 2 equal to what we can get, students? 2 omega 2. Yes, R by L plus 2 into square root of R by 2L whole square plus 1 by root LC whole square. Then what is omega 2? This is the expression for omega 2. R by 2L plus 2 to cancel, square root of R by 2L whole square plus 1 by root LC whole square. Is it okay? Okay, this is omega 2. Upper cutoff frequency I got. Yeah. If you want omega 1, what you can do? 1 plus 2 you calculated, we are getting the omega 2. If you want omega 1 means, yes, take the 2 minus 1. 2 minus 1. This is 2, this is 1. 2 minus 1 if you do 2 omega 1. 2 minus 1 you do, sir. That is 2 omega 1 you can get. 2 omega 1 equal to, which one is 2? This one. 2 into square root of, is it correct, sir? 2 minus 1 I am doing. That I am getting omega 2 cancel, 2 omega 1 you can get. 2 into square root of R by 2L whole square plus R by, sorry, 1 by root LC whole square. 1 by root LC whole square minus, yes, this is 1 is minus R by L. Minus R by L. Then what is omega 1? Omega 1 equal to, first I am writing this term, minus R by 2L plus square root of R by 2L whole square plus 1 by root LC whole square. This is the formulas, cutoff frequency. I derived the cutoff frequencies also. Omega 1 and omega 2 are the cutoff frequencies. If you do omega 2 minus omega 1, students, omega 1 I know, omega 2 I know. Then if you do omega 2 minus omega 1, finally are you getting this formula or not? Omega 2 minus omega 1, finally you can get the R by L if you want to check that one. Finally I am getting, this will be cancelled. In omega 1 this term, in omega 2 this term will be cancelled. That is R by 2L minus of minus R by 2L. That you get R by 2L plus R by 2L. That we are getting the R by L. Yeah, these are the expressions. Yeah, this is about today's session, students. In the next coming session, I want to continue with what is the selectivity in series resonance circuit, and later on we can solve some problems. And with respect to series resonant, it is RLC circuit. We can also define what is the damping ratio. Based on the damping ratio and quality factor relation also I want to give. Then after that we can solve some problems. Then I will give the what are the conditions for parallel resonance circuit, that is the RLC circuit, parallel RLC circuit, and we can define the what is the resonating frequency for tank circuit also. With that, resonance will be complete. Then tomorrow session I will complete the resonance. Okay, thank you, students. This is about today's session. Okay, thank you very much, everybody. I'm ending the session. Thank you, sir.